classes. So the circuit evaluation problem is complete for P, the class of polynomial time computable functions, so the class of efficiently computable problems. And if you add restriction to the circuit, it will be complete for smaller complexity classes. Well, for the purpose of this talk, well, if you restrict the depth of the circuit to be bounded logarithmic, so it's a log n to a fixed power I, then the circuit evaluation problem is complete for NCI, where NCI are problems that can be computed efficiently on a parallel machine. So formally, NCI are problems computable by circuits of polynomial size and depth log n to the I. So it corresponds to problems computable by a polynomial number of processors and in parallel time log n to the I. Because if you evaluate circuits using a natural strategy, then the number of processors you need will scale with the number of nodes in the circuit. And if you use the layer by layer evaluation strategy, then the depth of the circuit would determine the parallel time you need to evaluate the circuit. Okay, this NCI forms a hierarchy of efficiently computable problems inside P. They are problems that you can compute very efficiently if you allow parallelism. For example, NC3 are the problems that you can compute in log n cubed parallel time using a polynomial number of processors. And in this talk, we will consider these complexity classes and also the space complexity classes, deterministic logarithmic space and non-deterministic logarithmic space. So we will be considering a space and parallel complexity. The inclusions of L and NL into the parallel complexity classes are classical. For example, the simulation that any problems that can be computed in non-deterministic logarithmic space can be computed in log n square parallel time. This basically is the Savage algorithm, if you know. And if you don't know about the Savage algorithm, it's basically just fast matrix powering. So you want to raise a matrix to the nth power. You can do this in log n multiplication repeatedly. And if you implement this, this will take you log n square parallel time. Okay. And well, so it concerns space and parallel complexity. And if you suitably interpret circuit evaluation, well, it will have applications to database query algorithms, other models of computation, data flow models, or it concerns also, for example, big data computation. These complexity classes will have relations to big data computation. For example, in one model of big data computation inspired by MapReduce, it's known that if you separate NC from P, the parallel complexity class, from the sequential complexity class, then it means that in a certain theoretical model for MapReduce computation, certain problems cannot be computed there anyway. So it has applications elsewhere. Okay, these are the complexity classes that we care about. All right, then I'm going to introduce you the Pebble games. And in doing so, first, I want you to ignore the gate type of a circuit and consider the underlying graph of a circuit. So it's only a direct acyclic graph. And we will consider only a graph of bounded in degree, let's say degree 2, and it will have a unique sinc node. These are the direct acyclic graphs that we are considering. It is a circuit where you forget the gate type. Given a direct acyclic graph, you can play a Pebble game called the Black Pebble Game on it. It gives you an algorithm to evaluate circuit using little space. So it has two rules. First, you start with a fixed direct acyclic graph, and there's no pebble on it. And then you repeatedly apply one of the two rules to add pebbles or remove pebbles from the nodes. Every node can take at most one pebble. Okay. The first rule is that you can add a pebble to a node V, which is the red node here. You can add a pebble to it. If all immediate predecessors of the node have been pebbled, then you can add a pebble to it. That's the first rule. In particular, if you have a source node, then you can always add a pebble to a source node, because logically, all its immediate predecessors, which is none, are pebbled. Okay. So that's the first rule, to add pebble. The second rule is to remove pebble. You can remove a pebble at any time, regardless whether its immediate predecessors are pebble. You can remove a pebble at any time. So you repeatedly apply these two rules to add pebbles and remove pebbles. And the goal of the game is to place a pebble at the sink of the graph. And you want to use as few pebbles as possible. And if you interpret that a node as pebbled to mean that the value of the gate is remembered in memory, then the first rule means that if you want to compute the value at a certain gate, if you remember the values of the gates that fit into the gate, then you can compute the value of that gate. And the second rule means that if at any time you can forget the value computed, then any pebbling strategy is going to give you a space-efficient algorithm to evaluate the circuit, where the amount of space you need scales with the number of pebbles you used in the Pebble game. And by classical results that the number for any directed graph of bounded in degree, the number of pebbles you need to put a pebble on the sink node doesn't scale with the size of the graph. It scales with the size of the graph divided by logarithm of the size of the graph. So you get a saving of log of the size of the graph. This result in Pebble game translates to a result in complexity that any deterministic time t computation takes you at most space t over log t. It is obvious that it doesn't take you more space than time to compute, because it takes time to allocate memory. So a time t computation takes at most t space. But this is on the Turing machine model. But it is not as obvious that it takes you less space than time to compute. And this result is proved by a pebbling argument. So pebbling arguments give you upper bound, which also is the best known upper bound we know today. And pebbling argument gives you lower bounds in certain restricted cases. And this is what I'm going to talk about, is lower bounds by Pebble games. So these are the complexity classes of space and parallel time. We believe that they're different. We can't prove that. We can prove something if we add restrictions. Okay. One commonly studied restriction is the monotone restriction, is to disallow logical negation. And under that restriction, we can prove something. Marshall and RV proved that on the monotone circuit model, they proved that monotone NC1 is different from monotone NL by proving a lower bound for a directed connectivity on the monotone circuit. This result is improved later by Ran and Pierre in 1999. They reproved this result by a slightly different argument and to separate the monotone versions of two of the complexity classes. And Ran and Pierre actually proves the separation of the whole of the NC hierarchy under the monotone restriction. And to show that under monotone restrictions, there are problems that sequentially, they are inherently sequential that you cannot parallelize under the monotone restriction. And recently, Aaron, on a different combinatorial model, which I will get to in the later part of the talk.
Just to note, it's very hard to see the bar that's included but not equal to.
Oh, okay. Let me point out that all of these are separations. So in case you don't see it clearly, all of these are separations and our separation results. So Aaron proves that monotone L is different from monotone NL on a combinatorial model called switching network, which I'll get to later. It means a model that captures space complexity rather than parallel time. So this, he separates the space, the deterministic space, and the non-deterministic space under monotone restriction. And notice that this result is stronger than the previous result for directed connectivity. And this result separating space complexity is reproved and also generalized to the parallel complexity classes. So the hierarchy is separated and is separate from P under a monotone restriction. And there's one more result. And in all these results, there will be something that I will get to. Okay, one more result under certain other restriction, which I call semantic restriction, as opposed to the syntactic restriction of monotonicity. Under certain restriction, you can separate the parallel complexity classes and also separate NC from P under certain restriction. And in these lower bounds, some Pebble games appears, which I will get to later. For the moment, you just need to know that there are 3 Pebble games in the lower bounds. So they are respectively the Ross-Mackenzie Pebble game, because of the paper by Ross-Mackenzie, the Reversible Pebble game, and the Diamond-Toma Pebble game. And it turns out that actually it's the same Pebble game in the sense that for every fixed graph, the Pebble cost in any of the Pebble games agrees. And to prove this, we give you a simulation result that you given a strategy in one of the Pebble game, I can simulate it by a strategy in another Pebble game with no worse performance, using no more pebbles. So once you have the simulation results, then you show that the 3 Pebble games actually is the same Pebble game. So the point is that in these lower bounds, there are different Pebble games appearing, but it turns out actually it's the same Pebble game. So the scaling in complexity is under these restrictions is controlled by the same Pebble game. And it is also the best known scaling we know today for the upper bound. So it matches the upper bound under restrictions. So, and I'm going to talk about the Pebble games later, but let me mention one other. Okay, and this result is improved by Yovo, Tony, Robert, and Steve recently to the average case setting, and they are the okay. And
can I add another result to the list?
Oh,
there's an odd result of Sipser and Ponzio. Anyway, separating monotone NC1 from monotone L.
Monotone NC1 from monotone L.
Yeah, which is a little better than what we did in the first case.
Actually, what I'm going to say is that this picture is not accurate because you and this result actually separate monotone NC1 from monotone L just by this result, because they prove a low bound not only for directed connectivity, which is the complete problem for NL. They prove low bound for undirected connectivity, which by result of Ringel is that it is complete for L. Okay, so
at the time it was
okay,
the result was not.
It wasn't known that actually this separation is stronger. So to be correct, this result and this result are incomparable. But okay, okay, that's right. Thanks for the correction. Okay, cool. Okay, for another line of, I'm going to mention another line of research. For those who know that we will be considering a communication game called Kashmir-Wittenson game. The idea is that circuit depth is captured by certain the communication complexity in certain communication game, and by studying this communication game, we want to prove low bounds under certain restriction and a certain computational problem called universal compositional relation, which all talked about earlier, is suggested as an approach to separate NC1 from NC2, and it was okay, and certain separations under restrictions were obtained, and I want to say that this result considers a different problem. So it's incomparable, but morally it seems to be suggesting a stronger separation, that you separate the whole of the hierarchy and it's different from P. Okay, and in the last result under semantic restriction, the upper bound is given by one Pebble game and the lower bound scales with the other Pebble game. So it is crucial that we can prove that it's actually the same Pebble game so that you get a tight result. So, okay, I will get to that later. Okay. For the impatient, and okay, yes, let's mention that there's a new result here. That you are expected to see different complexities, most prominently parallel complexity and space complexity, and later I would talk about, we are shooting for a non-uniform lower bound, so it will have application to randomized complexity if we manage to get that. Okay, you will see it's motivated by communication complexity. It has certain connections to the symmetry complexity, and we will apply it to proof complexity. And the study of these problems is important because actually it also has applications to algebraic complexity, in the sense that if you manage to separate the complexity classes, then essentially you will have separated some of the algebraic complexity class. Basically, VP is different from VNP, modulo the generalized Riemann hypothesis by a result of Peter-Bergiza. Okay, so these are the okay, right. Okay, let me talk about the 3 Pebble games and their connections to different complexity results. The first Pebble game I'm going to introduce is the reversible Pebble game because it's the easiest to introduce. So it's similar to the black Pebble game. There are 2 rules in the Pebble game. You start with a graph with no pebbles on it. You repeatedly apply one of the 2 rules. The first rule is that you can add a pebble if all its immediate predecessors are pebbled. The second rule is that you can remove a pebble only if all immediate predecessors of the node are pebbled. So I reverse the arrow. And hence, you can apply one of the rules if and only if you can undo the change. So, and hence, this Pebble game is called the reversible Pebble game. And your objective is to put a pebble on the sink node and and clear the graph. So you leave only 1 pebble on the sink node and leave no pebbles elsewhere. And you want to use as few pebbles as possible. In this reversible Pebble game was motivated by the study of reversible computation. The reason to study reversible computation is that it is a theoretical possibility to reduce energy dissipation in computation. So if your computation is not reversible, it's irreversible, which means that you can erase memory content, you can forget memory content. Your computation is irreversible. You don't remember how you come to a certain computational state. Then you will have to pay energy to compute. But in theory, you can have a computation that doesn't use energy if you maintain reversibility in computation. So that's the motivation to study reversible computation, that you don't erase memory content anytime. If you make a step, you can always reverse the computation. And this is getting more important because, for example, observation-free quantum computation is inherently reversible. So people study reversible computation. And for this reason, Bennett mentioned the reversible Pebble game as an abstraction for reversible simulation of irreversible computation. It means the following. Imagine that you are given a program, normally written program. It is irreversible because it will overwrite memory content, it will erase memory, okay? So you want a compiler that's given an input program, compile it to a reversible program so that you will have the benefits of a reversible program. For example, it might be use less energy. So you want a reversible simulation of an irreversible program. You want this simulation to be as efficiently as possible. And as an abstraction, Bennett mentioned that reversible Pebble game is one way to achieve such a simulation, and different people studied the reversible Pebble game for this reason, to try to compile a normally written program into a reversible program as efficiently as possible. That's one reason people studied the reversible Pebble game. Another reason that we study reversible Pebble game is that somehow it pops up in the lower bound that I talked about earlier, that under Monton's restriction on the model of switching network, it is just there. And if you ask me why this is the case, the one-line summary is that determinism equals reversibility or symmetry. For example, Ringo proves that deterministic logarithmic space equals symmetric logarithmic space. In other words, if you are given a graph, an undirected graph, then to determine if one node is connected to another node, it takes you only logarithmic space to do that. That's the result of Ringo. And if you interpret that, it's saying that determinism equals symmetric logarithmic space. So, okay, that's one reason we study reversible Pebble game. And it turns out that this Pebble game actually is the same as another Pebble game called the Diamond Tumbler Pebble game. So in the Diamond Tumbler Pebble game, this is suggested as a way to design parallel algorithms, and is used by different people to design efficient parallel algorithms. It gives parallel speedups, well, if you allow an unbounded number of processes. And it turns out that a slight variant of this Pebble game exactly capture different complexity classes and inclusions, in the sense that the number of Pebble used in that variant characterizes the parallelism in NCI, NC, and P. So if you use log n squared pebbles in the Pebble game, then that would correspond to NC2. If you use a polynomial number of pebbles in the Pebble game, it corresponds to P. So that's why, so in principle, if you want to separate any complexity class here, then you can just you can do this by proving a Pebble game result. Then you will have separated the complexity class. That's one way of doing this. And also, these Pebble games will simulate the inclusion of non-deterministic logarithmic space in NC2, the Savage algorithm or the fast matrix exponentiation. Okay, so that's the reason people study the dimensional Pebble game. Oh, let me motivate the Pebble game. So imagine that you are trying to evaluate a circuit, this circuit. So we want to compute the value at gate A. So this is a circuit where you forget the gate type, and it's a diacritic graph. To compute the value at gate A, we will do it by divide and conquer. So we split the computation at a certain point. Let's say we pick C to split the computation, which means that in parallel, we will do the following. In one branch of the computation, we will compute the value at the gate C. In another branch of the computation, you guess the value of the gate C. Assuming you have got the right value, continue the computation to compute the value at gate A. And then you try to repeatedly break down the computation, and then you combine the results in constant time. That's the idea. Let me show you the recursion. So if you try to evaluate this circuit, first you want to compute the value at gate A. You break the computation at a certain point. In one branch of the computation, you compute the value. In another branch of the computation, you assume that you know the value, and then continue the computation. This is not the base case yet. You have to continue the recursion until you hit the base case. This is the base case. Likewise, in the second branch of the computation, this is not the base case yet. You have to recurse so that you can answer finish the computation in constant time. You want to minimize the depth of the recursion tree this way. And if you make a game out of it, you get the Diamond-Thomas Pebble game. It is a two-player Pebble game played by two players, the Pebble and Challenger, and they are playing against each other. They alternate to move. So Pebble will first move, and then Challenger move, and then Pebble move, and then Challenger move, Pebble move, and then Challenger move until the game ends. At first, Pebble will pebble the sync node of the circuit, and then Challenger would challenge the sync node. From that point onward, exactly one node will be called challenged. This is the sync node will be challenged at that time. Then in each subsequent round of the game, Pebble would choose some node to pebble. Let's say I pebble this node. Then the Challenger can choose to stay or to jump. For example, if the Challenger chooses to stay, the Challenger keeps challenging the node that the Challenger was challenging. He stays at the point where he was challenging. If he chooses to jump, then the Challenger jumps to the new node that is pebbled by Pebble. So the Challenger only has two choices. You don't have to remember the rules of the game. I will remind you the rule of the game when they are needed. I just want to give you a flavor of the Pebble games. In particular, notice that this is pretty different from the black Pebble game or the reversible Pebble game. It's a two-player Pebble game. But it turns out that the number of pebbles needed in this Pebble game equals the number of pebbles you need in the reversible Pebble game. And
it's two players, but you could describe it as a one player where you just look at the maximum number of pebbles.
Yes, you can. It will be important. Yes, it will be important when you try to prove the equivalence. Yeah. Okay. And Pebble wins if before she moves, the challenge node has all immediate predecessors pebbled. This is the configuration that makes this the end of the game. So it's not hard to see that Pebble will always win if she keeps pebbling every node in the graph. And the Challenger can, at best, to delay the inevitable. And the number of pebbles that the Pebble needs to force a win against any Challenger will be the Pebble cost of this game. Okay. This is the Diamond-Thomas Pebble game. It turns out that this is the same Pebble Game as another Pebble Game introduced by Ron and Pierre, the Ross-McKenzie Pebble Game. This is used to give depth lower bounds to Morton circuits, and is motivated by decision tree complexity of search problems. In short, the game tree more or less will give you the decision tree. It has applications to prove complexity because the study of this Pebble Game inspired a certain unsatisfiable CNF called Pebble contradictions, which I will introduce soon. And it gives many separations and trade-off results in different models of proof complexity. And in particular, it turns out that the Pebble course in this Pebble Game exactly characterizes the depth of resolution refutation of Pebble contradictions, which I will explain in a moment. Okay. All right, and okay, this is based on the work by Alistair Urquhart, who proves a lower bound, and then basically I tighten it to an exact bound. Okay, so this Pebble Game. To introduce this Pebble Game first, I have to explain what Pebble contradictions are and also what resolution refutations are. Okay, Pebble contradictions are unsatisfiable CNF constructed this way. So it has a graph structure. Given any graph G, I can give you an unsatisfiable formula in conjunctive normal form that has the structure of the graph G as follows. The idea is that first I will allocate one variable in the CNF per every node in the graph G, and then we'll add clauses so that the following will be implemented. I want, for every source on the graph G, I want the source variables to be true. I want this. And I want the truth values to propagate through the graph. And finally, I want the sink variable to be false. Intuitively, this can be done. Okay, let me give you an example. So imagine that you are given this graph. For all the source node, for example, D is a source node, I will add a clause to make this variable true. So to do that, I add a clause with a single literal D. If you want to satisfy this clause, the only way to satisfy this clause is to make this variable true. So this way, I make sure that D is true. Likewise, I will add a clause for every other source node. And then I want the truth value to propagate through the graph in the sense that I want, if D and E are true, then B has to be true. To do this, I just have turned the implication into disjunction. Okay, and do this, I propagate truth for every node. And finally, I add a clause to say that the sink has to be false. And this CNF in conjunction of all these clauses will be the Pebble contradictions corresponding to the graph G. It turns out that this CNF, if you consider the resolution refutation depth of this CNF, it will be exactly characterized by the Pebble Game. So the resolution refutation of minimum depth for the Pebble contradiction will be exactly characterized by the Pebble Game. And resolution refutation is a well-studied proof system. Its lines are clauses. So A or X, this is a clause, is a disjunction of literals. This is also a disjunction of literals. If you have two clauses where they differ by one complementary variables, then you can do a resolution step. And assuming they share no other complementary variables, then you can do a resolution step to get the resolved clause. This is one step of the resolution step. And you keep applying this resolution step until you get a contradiction, the empty clause. So let's consider a resolution tree you get this way. If you manage to get a contradiction, at the end you get the empty clause. And at every internal node of the resolution tree, you will be resolving on certain variables. For example, here you'll be resolving on the variable B. Here you'll be resolving on the variable C, and so on. I'm trying to locate a deep branch in this resolution tree. I want to show that this resolution tree can't be shallow. So to do this, I'm going to come up with an adversary that does the following. The adversary will maintain a partial assignment and assignment to a subset of variables while maintaining the invariance that the current clause will be falsified. So the empty clause cannot be satisfied. That's fine. If I want to falsify this clause B, I just have to make B false. That's easy. let's say I want to locate a branch here. So then I want to falsify this clause. Then the adversary maintains a partial assignment to falsify this clause. So in other words, to make B false and also to make C true. And keep doing this until you locate the branch in the residue tree. And if you want to do this, when a branch grows to the leaves.
Can you go back to this picture? I think it's probably worth saying just because it's flipped and also.
Yeah, I'm just assigning so that it's flipped, yeah.
It should remind everybody just lower bounds on decision tree, Boolean decision tree, because really, if you flip it and you think about the decision tree labeled by the variable that is being resolved, it just looks like
it's just a decision tree, yes.
Oh
yes, it is exactly the decision tree, yeah. So this is a decision tree for you to search for a clause falsified by a certain assignment.
So okay. It's just picking an assignment which has a long path in the decision tree. It's the same spirit. Another thing I want to mention, I don't know how many people have seen refutation in general, but the main goal is to prove that a set of clauses is unsatisfied. You start with them as sort of axioms, and then you derive more and more clauses until, if you derive the empty clause, then you prove that they are contradictory. And exactly this rule says assume that you could satisfy with the same assignment A or X and B or X bar. Clearly, if you could satisfy both, you could satisfy the result. So that's the spirit, that's the intuition behind resolution step. It's a sound proof system. So.
Yes, right. Residue refutation is a proof system. It has only one step. It's a sound derivation rule that if you have an assignment that satisfies both of these clauses, then you will have an assignment satisfying these clauses. And anyway. Okay, so we want an adversary that maintains a partial assignment that falsifies the clause. And if the partial assignment does not falsify any clause, any axioms, any clause of the Pebble contradictions, then the branch must grow deeper. So we want a way to locate the deep branch in the tree. So remember that to falsify a clause means that I have to set source variable to false, or for an implication, I have to set the B and C to be true and A to be false to falsify it, or I will set the thing to be true. And the adversary wants, whenever a variable is created, answer true or false in such a way that try to avoid falsifying a clause from the Pebble contradiction. If you make a game out of this, you get the number of answers you get will lower bound the depth of resolution refutation. If you make a game out of this, you get the Ross and McKenzie Pebble game. I don't know if this is the original motivation for introducing this game.
We didn't think about it as a Pebble game.
Oh, well, anyway. Anyway, so this is at least one way to define the Ross McKenzie Pebble game is that if you make a game out of the adversary, the play between the adversary and someone trying to give you assignment, then there are two players, the Pebble and the colorer, and they're playing against each other. They alternately move, the Pebble move first, and the colorer move, and the Pebble move, and the colorer move. In each round, the Pebble will choose a node to Pebble, and the colorer can choose to color it true or false. Here, true is represented as blue, and false is represented as red. And the Pebble wins if before she moves, some false node has all immediate predecessors true, because you will be falsifying an implication, or you'll be falsifying a source node variable, or you will be falsifying the sink variable. Then, colorer will always lose. The best he can do is to delay the inevitable. And the cost, the number of pebbles you need is, the cost of the Pebble game is the number of pebbles needed by the Pebbler to force a win against the colorer. And it is, what I have shown you is exactly the proof that it exactly captured the depth of resolution refutation for the Pebble contradiction, because the colorer strategy gives a lower bound, and the Pebble strategy gives you an upper bound. That's sorry?
The colorer has to color.
Yes, I allowed the color. Oh no, that's a good point. When I'm defining like this, I require the colorer also to color the thing. I require, but in order to make this game exactly corresponds to the diamond topology game, I have to modify the game. I think that's I will add the initial step to make it more like a diamond topology game. So I will add an initial step, because in the diamond topology game there's an initial step. So I will make sure that the pebble needs to do something and color needs to do something at first, so that it will look exactly the same as diamond topology game. Well, the takeaway point is that, well, there are two players, they are playing against each other. Pebble moves, and then her opponents move. The pebble moves, her opponents move. At first, pebble do something, and then her opponents do something. Each round, pebble do something, her opponents do something. And you can see that syntactically, the two games are basically the same. So let's show that they're actually the same game. So, right, so let me show you that diamond topology game actually is the Ross-Mackenzie Pebble game by giving you a simulation argument. You can think of this as a reduction in combinatorial game. So what I'm going to do is that, when you give me a color strategy in the Ross-Mackenzie Pebble game, I will give you a challenger strategy in another game, the diamond topology game, such that if in the simulating game, in the diamond topology game, if it is over, then the original game is also over. And this will show that the diamond topology Pebble game requires more pebbles than this Pebble game. That's the plan. Give a simulation strategy. All right. What we want to show is that, given a color strategy, I come up with a challenger strategy with no worse performance. Well, so here's the transformation in strategy. Is that whenever a node is changed, then you check, assuming at this point a certain node is changed in the diamond topology Pebble game. Now, if certain node is pebbled, then you think what the color strategy would do, and then the challenger will try to respond that if the colorer in the Ross-Mackenzie Pebble game colors it false, then the challenger in the diamond topology Pebble game would jump. Otherwise, the challenger would stay. This is a complete description of the simulation of strategies. So I want to show that if the diamond topology Pebble game is over, the Ross-Mackenzie Pebble game is also over. This will establish the lower bound. Notice that the simulation is defined so that the following invariant is maintained, that the charged node is the earliest false node. Because whenever a node, let's say this node points to this node, this is a predecessor of this node. If some pebble node becomes false and is a predecessor of the charged node, then the challenger will try to maintain the invariant by jumping to the node, so that after you jump, the earliest false node will be charged. That's the transformation strategy, is to maintain this invariant. If you maintain this invariant, then if the diamond topology Pebble game is over, it means that the charged node is pebbled and all immediate predecessors are pebbled. It means that in the Ross-Mackenzie Pebble game, the current node is false and all immediate predecessors are true. So the Ross-Mackenzie Pebble game is over. So this proves the lower bound.
So implicitly, you're also defining sort of a mapping between strategies for the other pair of players, and arguing that covers all possible.
Yes, it covers all possible. It's isomorphism. That it maps strategy to strategy, preserving performance. Okay, this shows you one inequality. With more work, you show the reverse inequality. Then you establish that the diamond topology Pebble game is exactly the Ross-Mackenzie Pebble game. With even more work, you show two more inequalities. Then you show that these two Pebble games is equal to the reversible Pebble game. So that's the idea. All right. Okay, wrap up.
It's pretty amazing that all these things existed for 20, 30 years, almost all of them, and nobody knows.
Oh, it's even more amazing that in one of the papers studying the reversible Pebble game, in the introduction, the author says, well, there are other Pebble games they studied, like the diamond topology Pebble game, but actually it's the same Pebble game. So anyway, so
you probably know the joke to tell at this point is what Pippinger has a survey on Pebble, which is very old, doesn't have this stuff, but it starts quoting something Karp said about Pebble. What Karp said about Pebble is you're pebbled when you don't have enough grass to be stoned.
Okay. So, all right. Yeah. So we show claims that the three Pebble games are equivalent. It has relations to computational complexity for using restricted depth lower bounds, and it has applications to prove complexity. It captures the depth of residual permutations for Pebble contradictions. And you can also study the problems of complexity of Pebble games. So it turns out that the three Pebble games are p-space complete. And in an upcoming work with people at KTH, we actually show that even for graphs of bounded fan-in, these Pebble games remains p-space complete.
What is the biggest gap between any one of these games and the black Pebble game?
Oh yes, the biggest gap, I think. So we actually we show a lower bound that the question is, what's the biggest gap between black Pebble game, black irreversible Pebble game, and the reversible Pebble game? I think it's a multiplicative factor of log n. We can show that. Log n. And all right.
So that's an upper bound.
And that's a lower bound. And I think someone claims an upper bound, and we are trying to recover the proof from somewhere anyway. I know.
Yeah, of course, but no, there's nothing better than n over log n.
Okay. Okay. Well, let me briefly mention that. Well, we try to separate complexity classes. So actually, there are other approaches of separating complexity classes that does not mention Pebble games. Briefly mentioned. Well, but it actually is somewhat related at a very high level, related to what I talked about earlier. For example, one approach to separate ACC0 from P is to study communication complexity on the multi-party communication model to study the computational problem of pointer jumping. And this pointer jumping problem is very similar to the iterated indexing problem, where the information flow in a reverse direction. So it's similar in spirit. And when you are considering communication complexity, there are other suggestions that maybe if you consider different way of distributing information, then you may be able to separate NL from NP, NC from P, whatever. And the Pebble games, actually, the diamond temporal Pebble game captures not only the depth of a circuit, it captures also the size of a circuit. So maybe you can study size and depth, and there are other people suggesting to study size versus depth of a circuit, that it may give some separations. And also, we will talk about some combinatorial invariance, and it will and combinatorial invariance is suggested in some way to separate algebraic complexity classes. Okay, so.
What is the result that they are also Recursion paper showed on then from extending Recursion games?
Oh, this one is about refereed. Yeah.
It's just a variant of, you can think of it like the multi-party communication complexity number of forward model that applies, let's say, to branch code. There's another variant of distributed input, so that,
I
and where there's a non-deterministic like Uber or something.
Yeah.
And then you get, you can separate other classes using this kind of way. It's not necessarily the best way to go about it. Just a combination.
Right. I think that would be a good point to have a break.
Before or after your question?
Well, my questions is the questions to the first part. So have a break right after the questions. So I mean, any more questions?
Okay. It's questions you asked. Okay, good. So we'll take it. This is some low bounds.
Yes. So I'm going to talk about proving lower bounds under the monotone restriction by Fourier analysis. All right. And it's a joint work with Aaron. So these are the complexity classes that we care about. We believe that they are different. We can't prove that they are different. We add restrictions, and to see what we can say, if you add the monotone restriction, which is to disallow logical negation, we separate almost all of them. We separate almost all of them, except here, except this one I think is not known. separate NL and NC2 under multiple restriction. All other complexity classes have been separated. And it started by, let's focus on the high N, Morton P versus Morton NP. It started by work of Reversible. He proves that the K-clique problem, the NP complete problem of K-clique, requires super polynomial size Morton circuits to solve. Oh, actually, N to the log. Yeah, I think I can get a more. First, no, that's true. I mean, N to the log, and then it would correspond to at big omega of log square n. Okay, but yeah, he proves the size lower bound, and if you translate it to the depth lower bound, which is to take logarithm, so he proves at least a super logarithmic lower bound. I think is big omega of log square n. And later, is improved, the depth lower bound is improved to a small polynomial. And actually, Ran and Pierre pins down the dependence on K, that it should scale at least as K log n. The depth of a Morton circuit solving K-clique has to be at least K log n, when K is a small, at most a small polynomial. So this is about parallel time. If you consider a combinatorial model that concerns space, and also by using standard translation from space to from parallel time to space, then you will have the corresponding lower bounds on Morton switcher network size, which I will introduce in a moment. The point is that you will have a quadratic loss. So a switcher network of size exponential corresponds to polynomial space. So everything here should be considered at an exponential scale. In other words, you should take logarithm to understand how it relates to space. But other than that, you can see that you have a quadratic loss when you translate the depth lower bound to switching network size lower bound. And the quadratic loss basically is, again, due to the loss of simulation when you go from NL to NC2. The Savage algorithm, or more accuracy is first proved by Borodin. Okay. So you have a loss when you translate from parallel time lower bound to space lower bound under a Morton restriction. And in earlier work, we get a tighter bound, for concerning space under Morton restriction. And today I'm going to talk about this result, that the K-clique problem requires Morton switcher network of size 2 to the K log n. In other words, n to the K. Okay. So let me introduce the model, the switching network model. A Boolean function, we will be considering Boolean function. A Boolean function has the following problem. I am trying to fix notation. It has n input bits, and you output 1 bit. And the n input bits will be denoted by variables xi, and it has 2 corresponding literals, the positive literal and the negative literal. Okay. Once you give me a Boolean function, then I can give you a switching network to compute the Boolean function. Switching network formally has the following data. It is an undirected graph G prime, and with 2 distinguished nodes, S prime and T prime. It's called the source and the sink. And there's a labeling function on the edges to label every edge by a literal. For example, label this by positive x3 and label this by negative x2. Once you specify all this information, this specifies the switching network model. And then let me talk about how it computes function. So it's computes by reachability. Then fix an input instance, a specification of n bits. Then an input instance reaches a node on the switching network. If there's a path to bring or to connect the source S prime to a certain node, label with literals on the next. I will give you an example right in a moment, and you'll see that. And the point is that once I define reachability, then the computation means is defined by whether the input instance can reach the sink node. In other words, an input instance is accepted by the switching network if only if an input instance reaches the sink node. Okay, so let me give you an example of reachability, and you will see. Here's a random example. In this instance, let's say there are 5 variables, and this is the truth value. So the edges that agrees with the input instance will be usable or will be live. and you want to use the live edges to connect the source node and the sink node. So you can see that x is false, x1 is false. So negative x1 can be used. Positive x1 cannot be used. For example, x2 is true, so positive x2 can be used, but negative x2 cannot be used. And once you give me an instance, I keep all the live edges and discard all the dead edges. And then I check whether there's a path to connect the source node to the sink node. That's the computation on a switching network. And
the switching, just to compare it to what people are probably more familiar with, which are the branching programs, there are two differences. Variables sit on the edges and not on the vertices, and the other is that it's an undirected graph.
yes,
And not a directed one. But every instance gives you a subgraph of this graph, and you just look at the subgraph and check whether S prime is connected to T prime. Then
Yes.
the function should be 1, otherwise it is.
yeah, that's right. Okay, I said this is a model to capture space complexity. The reason is that a graph like this of exponential size would correspond to polynomial space. Or in other words, if you want to consider logarithmic space, then you consider polynomial size switching network. And to see that, you just have to interpret every node of the graph as a state of a computation, and every edge as a transition of the computation. Then a logarithmic space computation can have at most a polynomial number of states, so it will correspond to polynomial size switching network. And the reason that we are allowed to use undirected edges instead of directed edges in a switching network is because of the Reversible wrinkle. That's one way to see that.
Yeah, but I mean, even beforehand, it just represented the projection reductions to undirected connectivity.
Yes, undirected connectivity, but it will correspond SL, symmetric logarithmic space. But we didn't know that it corresponds to deterministic logarithmic space, and it's because determinism equals symmetry. But
So every log space algorithm can be translated, can be implemented using this model?
yes, this can simulate every logarithmic space computation has a polynomial size switching network. Yeah.
With symmetric or deterministic or even symmetric algorithms.
Yeah. Okay, so here's one example. Let me show you another example just to make sure you get it. For example, in this instance, you keep all the edges that it agrees with the input and discard all the edges that doesn't agree. And since there's a path connecting the source node and the sink node, so this instance is accepted by the switching network. That's all I want to say. Okay, good. For later part, I want you to focus on the truth table at every node on the switching network. I will remind you later, but that's an important notion that we will be studying the truth table at every node. That at the node, let's say this node, the truth table is the enumeration of the truth value of to specify for every instance whether that instance can reach this node. Then we will consider the truth table of all nodes in a switching network. Okay, okay, good. This is a switching network. We are considering a restriction, a pretty severe restriction called Morton restriction on a switching network that we disallow logical negation. Formally, it means that we only allow you to label every edge by a positive literal. You're not allowed to label it by a negative literal, and hence it computes only monotone functions. In particular, in this talk, we consider k-clique problem. I know you must have heard of the k-clique problem, but I'm going to fix notation.
Even for the non-monotone case, there is one lower bound.
Okay.
There are both lower bound
Yes.
like n log star
Yes.
for majority. But that's the best known. The best we know for a non-monotone switching network lower bound is just slightly simple linear.
Yeah. All right. Okay. After introducing the model, then here's the problem, the computation problem, k-clique. The input is a subset of edges, and you want to output if the graph has a k-clique. In other words, k vertices, such that all distinct vertices are adjacent. Good. For this computation problem, here's an example of a monotone switching network for the k-clique problem. In particular, for 4 nodes, I want to solve the 3-clique problem on these 4 nodes. For example, for this instance, if you keep all the edges that is consistent with the red edges here, consistent with the edges in the input graph. So note that there are 2 graphs going on, one graph from the problem and one graph from the model. This is from the k-clique. We want to compute k-clique on this graph, and we use a graph to compute k-clique. This graph is the switching network. So please, Yes, and for notation, I am going to denote objects of the problem with unprimed objects, with unprimed letters, and to denote objects of the model, the switching network, with primed objects, S prime, T prime, G prime, V prime. So, okay, whenever you see a prime, it's a model, the switching network. Whenever you don't see a prime, it's something from the input instance. You can see that this instance can reach the sync node. So this instance is accepted by the switching network. For another instance, this instance cannot reach the sync node. So this is not accepted by the switching network. Okay, sorry, I realized these two nodes are also reachable from the source. Okay, good. So this is the monotone switching network for K-click. It's not hard to see that for K-click, there are monotone switching network of size n to the k to solve K-click by the guess and check algorithm. You guess a K-click and check it, and the size will be n to the k. In other words, the space required will be k log n.
More generally, a monotone formula can be simulated by monotone switching network.
Oh, and you use monotone. Okay. Yeah. Okay. Yes. So okay. So it has an upper bound, and in this talk we are going to show a matching lower bound. So, all right. Here's the plan of attack. We are going to give a bottleneck argument. I'm going to come up with a function, let's say beta. It maps K-clicks to nodes on the switching network, to map objects of the input to objects on the model, in such a way that for every node on the switching network, not many input instances are mapped to it. So for every node on the switching network, there are only few K-clicks mapping to the node. Well, if we manage to do this with good enough parameters, then we know that the number of K-clicks is n to the k. So it means that the number of nodes on the switching network is also n to the k, assuming there are really few clicks mapping to every node.
This view will also be of size something like
it's growing, k to k. It will be k to the k.
K to the k only. Okay.
K to the k. And hence we need that n is polynomially bigger than k. Okay. So this is the plan of attack. All right. We are going to analyze the following instances of K-click. Yeah. Oh, okay, good. So in complexity theory, this is normally called the bottleneck argument. It appears many places, like in communication complexity, in proof complexity. Another way to put it is like double counting argument or basically principal principle or whatever you call it. This
the charging mechanism. You want to charge, every input. You want
so let's say
to a node in the network. If you can charge it in such a way that every node is charged with very few clicks.
Let's say at most one. If every node is charged with at most one click, then you have a lower bound of n to the k. But it works even if you charge a bit more than one. So that's, yeah. Yes, that's the bottleneck argument.
It's not enough of an explanation. This is something we wish to do.
And, well, for example, I think the proof that all talk about earlier on universal compositional relation can also be cast as bottleneck argument. Okay, good. So this is the plan of attack. Okay, we are going to analyze the following instances. The following yes and no instances of the graph. In other words, instances that contains a k-click and instances that do not contain a k-click. So we will be considered, since we are under the monotone restriction, we will consider the mean terms of the k-click. In other words, a graph contains exactly one k-click and no edges else, because this is a yes instance. This contains a k-click, but if you take away any edge, it becomes a no instance. It doesn't contain a k-click if you take away any edge. So we will consider instances that have exactly one, they have edges in exactly one k-click and no edges elsewhere. It can be identified with a click P of size with k vertices. The identification goes as an edge is in the instance corresponding to the click if and only if both vertices are in the click. Well, I assume that is joint. Okay. These are the yes instances that we are analyzing. And for the no instances, we will study a structured no instance many people study that is to consider k minus 1 colorable graph. So it will be identified with coloring. A coloring specifies for every node a color. Since the graph is k minus 1 colorable, so it is a mapping from vertices to k minus 1 color class. And the identification goes as follows, that given any coloring, an edge is in the instance if and only if it doesn't violate the coloring. In other words, that the two endpoints receives different color. Because if you get a graph, if fix a coloring, and then you add edges as long as the two endpoints receive different colors, then every coloring will give you a graph. This graph will by definition be C colorable, will be colorable by C. But if you add any edges to it, then it will become not colorable by C. So it's a maximal in a sense. It's a structured instance that is maximally colorable by C. But if you add more edges, it won't be colorable by C. It is a no instance because a k-click cannot be a k minus 1 colored.
It's the same yes and no instances with
By Reversible many lower bounds concerning clicks, not just monotone. Okay.
It's almost no loss of generality to use them when you
When we are under the monotone restriction, it's without loss of generality. Well, this actually is not quite. This I'm not sure. Coloring. This is without loss of generality. This one, the choice of the no instance is not maximal. Okay.
if you can compute, if monotone model is correct on this, then it will be correct on all others.
Is it? I'm not sure because, in other words, there may be graphs that does not have k-click, but it's not. Would it? So.
Either contain one or the complement contains the other.
Okay. But let me mention that
Not taking all colorings.
we are taking all colorings. So the graphs will be repeated. Every graph will be, yes, this is important.
Good.
We are taking all possible colorings. So
But you are right.
different colorings can correspond to the same graph. We are not analyzing graphs, we are analyzing colorings. This is important because two different colorings, if they differ by the permutation class, they will give you the same graph, but we consider them different objects of analysis. Okay. If we consider this class of no instances or this coloring, then
how is the input represented if yes instances are graphs and those
also graphs.
coloring?
We will be considering graphs.
Oh, but just no instances of coloring.
Because for every coloring, you can read off a graph from a coloring.
Yeah, what I'm asking is, are you representing
We are represented as coloring.
a string of bits or a string of values from one
Think of this. It's just a k minus 1 parallel graph that the coloring is.
Oh, I see.
Okay. Okay, here's how we analyze this formally. We will be considering k minus 1 coloring of vertices. And we will consider the following space, script C. Script C is a collection of all strict C. Upright C. Upright C is a coloring, a k minus 1 coloring on the vertices. It maps colors to k minus 1. So this space, the collection of all such colorings, can be identified with k minus 1 to the V. Script C is this space, all possible k minus 1 coloring on the graph. With this, on this space, we consider vectors that maps script C to complex number. In other words, if you give me a coloring, I will give you back a complex number. I consider those vectors. The vectors that if you give me a coloring, I give you a complex number. We will be considering these vectors. For simplicity, I call them script C vector. Okay, that is indexed by a coloring, k minus 1 coloring. And then we would an example of such a script vector is the reachability table on every node. It is an object that if you give me a coloring, I can give you a complex number. If you give me a coloring, I first compute a graph corresponding to that coloring. This will be an instance. Then I can check whether that instance can reach a node A prime. If it reaches, I return yes, 1. If it doesn't reach, I return no, 0. So the reachability table can be identified with a script C coloring, with an object that if you give me a coloring, I give you back a complex number. Actually, I will give you back 1 or 0. I give you back the truth value, whether the node instance corresponding to that coloring can reach the node A prime for every node in the switching network. This can be identified with a vector. And then we are going to do Fourier analysis of these vectors. Good. And okay, this comes with an inner product, which is given two vectors that, like this, indexed by coloring, is the expected value inner product. And this is, I'm spelling out the expected value as weighted sum. And you can think of this as average the reachability over the class of colorings, the node instance we are analyzing. So we are going to analyze it in this inner product space, okay? Once we've defined the inner product, then we can do Fourier analysis. Using the standard Fourier basis, I'm just fixing notation that the Fourier character chi of U, U is also an object in the same space. It syntactically is the same thing that U is a thing that if you give me a coloring, U will give you back a complex number. And you have the character, the chi of U is the standard definition where omega is the k minus first root, primitive root of unity. The key property we need from the Fourier basis is that it forms an orthonormal basis, that the inner product between two characters is one if only if they're the same character. Okay.
Going back to average reachability, you meant that when you take the inner product to RA and RA prime, or RA prime and RB prime.
Oh yes, you can do something that doesn't correspond there. I'm just give you. Yeah, you can think of it that way. I mean, if you, I mean, the point is average. We are going to average out things, and we are going to average out the reachability to a node. There's.
Could you just go back to the
I mean, yeah.
Okay, so when you say average reachability, you're talking about when F and G are
Reachability vectors, but which will be the no? Yeah, this is technically if you don't fit in reachability vector, then this doesn't correspond to reachability. But if you fit in reachability vectors, which will be the case in our analysis, then it corresponds to average reachability.
But you really need the correlation with reachability.
Yes, you can think of it that way. So yeah. Okay. Although our point is that we always fit in, we almost always never fit in reachability at the same time, RA prime and RB prime. We only fit in one at a time. So what you will see.
So omega is in this case what root of it?
K minus first.
K minus 1 is the number of colors, right?
Yes, number of coloring. So just to be, to fix it. Okay, good. This is standard Fourier analysis. Then we recall, Yes, so we want to implement this strategy of coming up with the bottleneck function that maps cliques to nodes on the switching network so that not too many cliques are mapped to every node. Okay, that's what we are going to do. We are going to come up with something that has 4 properties. We are going to come up with, we want to do the following. For every clique P, I want to construct a vector G prime, a C vector, script C vector G prime. So for every clique, I'm going to construct a vector, the script C vector. In other words, if you give me a coloring, I will give you a complex number. This G prime has to satisfy 4 properties. And I'm going to introduce them one by one. I want that for every clique P, there will be a certain node on the switching network. Remember, primed objects are on the switching network. For every unprimed objects are things of the input of the problem. For every clique, I will find a node in the switching network. That's where the bottleneck is going. I will find a node in the switching network such that this vector will have a non-negligible correlation with the reachability table at that node. This is the bottleneck node that you're doing lots of work relative to this clique P. So the vector will have large inner correlation, large response with the truth table or reachability. It will be a certain non-negligible factor. Okay, that's you are doing. Non-negligible 1 over size of the switching network. That's good enough.
It's not work. Correlation is non-negligible. It's not the work involved in proving it, but it's.
Okay. Sorry. The work done by the switching network.
But this
for this click P is non-negligible. By work, I mean.
To be expected if there has to be a path between.
Oh yeah, okay.
Prime and
Well, okay, good.
you know,
If
one
you think it's obvious, that's even better.
No, I'm not saying it's obvious. It's just intuitive.
That's what we try. We want to do. Yes, that's the intuition. We want to show. That's exactly what we are trying to show. Work as in the sense of you have to do work. The switcher node has to do work for this click P, and it's not shared with other click P.
It's consistent with the Reversible approximation method when applied to switching networks, monotone or not. You get a cover, but okay, you don't know.
Yeah. Okay. Okay. Good. That's the first property. The second property is called locality. It means that for every click P, I want to find a vector GP. This has to depends only on the coloring on P. In other words, it means that if you fit in two different colorings, but the colorings agrees over P, then GP has to return the same value. So by agreeing, it means that so remember a coloring specify colors on every node on the graph. So it also takes something. The coloring takes a vertex and returns a color. A k-1 thing. They agrees on the coloring on P, on the click P, if they assign the same colors over P, and they disagree only outside of P. So if two colorings, they color the vertices of graph. If they agree on the click P, but they can disagree outside. They can assign different colors to vertex outside of P. If they agree on P, then the vector has to return the same value. This means that the vector depends only on colorings on P. Okay, it's local to P, P local. Sorry?
What is the first line?
Sure. What I want to do is for every click P, I want to construct GP satisfying four properties. The second property is that the vector depends only on P, or if you fit in two colorings that agrees on P, then it has to return the same value. And to a Fourier analyst, it means that the Fourier coefficients is supported on frequencies subset of if the support of U is not in P, if the support of a Fourier of a coloring in the Fourier domain is the set of vertices receiving non-zero color. In the Fourier domain, syntactically, it's the same object that they take coloring. U is an object, has the same syntactical object as a coloring. It receives a vertex and returns a k-1 color. The support of a free Fourier frequency is the set of vertices receiving non-zero color. So the Fourier coefficients at any frequency will be 0 if the support of the coloring is not subset of P.
And in particular, they'll all be degree K polynomials.
Oh, yes, they will be degree at K polynomials. So, and these two are equivalent, A, B, and B. Okay, that's locality. And the third condition is k-1 wise independent, or at it, which means it will be uncorrelated with any functions depending on few variables. So if f is a function that depends on at most k-1 variables, then the vector GP has to be uncorrelated with f. And to a Fourier analysis, it means that if the support of a coloring is at most k-1, then the Fourier coefficient will be 0. Okay, good. Together, condition 2 and condition 3 will control the Fourier support of the. Will be homogeneous degree K polynomials. In other words, the only Fourier support, the only Fourier coefficients which is non-zero will precisely be of size K. Okay, up to 1. I will fix that. Okay. If these two are satisfied, then you can only have Fourier coefficient at P. Okay, good. And hence, for different P, they will be orthogonal, which we will use later. So the point is that condition 2 and condition 3 together implies orthogonality of the family of GP, which means GP1 will be orthogonal to GP2 for different clicks P. That's what we want. Okay, that's the third condition. The fourth condition is that it's short. That the norm of the vector is bounded by K to K. This will be the number of K clicks that can map to a single node. And
the 2 and 3 implies that they are monomials?
they're orthogonal.
No,
Actually, so
Only on P.
so okay,
There's
if
no
we
K
actually get 2 and 3, then it will be monomial. But we actually don't get this far. I will show you how. I mean, I will show. This is not exactly we are getting, but let's assume we are getting this. I will show you slight technicality. Okay, good. If we have these 4 conditions, then we can prove a lower bound. Here's how.
What is the four?
Oh, the 4th condition is short. The 4th condition is short.
Doesn't it mean that GP is just doesn't 2 and 3 together mean that GP is just a character on P?
So,
The character
Yeah.
associated with P?
if you satisfy 2 and 3, yes. But we actually will be satisfying something slightly different. Okay. So let's assume that we actually satisfy all 4. Okay.
Can you tell us or remind me why the Fourier transform of GP should be an object that makes subsets of
The,
vertices?
yes. The reason is that we are doing Fourier analysis over script C vectors. The dual of that space is self-dual. It's the same space. So the frequency will be an object of the same syntactic form. It will be a K minus 1 coloring. U is a K minus 1 coloring. So in particular, U,
Oh, use a K-1 color.
it will, it,
But why, make it look like it's a set of vectors.
oh, sorry, this is a typo. It's a support of U, is not subset. Sorry, I make a mistake here, sorry.
Oh, it's a support. So,
This is correct. This is wrong. This is correct. I have to use support of.
okay, so what's the support of a color?
A support of a coloring is the set of vertices receiving non-zero color.
Sorry, maybe it's a foolish question, but in Fourier analysis over non-binary domains,
Okay.
can you still associate the Fourier domain with sets? Don't you need to associate it with vectors?
Oh yes, one usual way to associate a set to a Fourier frequency in a non-binary domain is to consider its support. It is not, yeah, there's a usual way of doing things. Okay, 1, 2, 3, 4. So if you have 1, 2, 3, and 4, then we can prove a lower bound. Let me show you. So I have said 2 and 3 implies that GP is orthogonal.
Can you go back? Yes, it's continuing the same question of Andy. So U is supported on K minus 1 coloring.
So U is supported on K minus 1 card. U is, oh, I see. Oh, it seems like there's, okay. At the end, we actually make it only K minus 2 Y's independence instead of K minus 1 Y's independent.
No, that's not what I'm asking.
So-
So support of U, how is the support of U defined again?
Support of U are the set of vertices receiving non-zero color.
Non-zero color, but 0 is not a possible color, right?
0 is,
You have 1
Oh,
K minus 1
I will, let's define 0 to K minus 2. If it is 1 to K minus 1, then not 1.
And those that receive non-zero.
Yes, non-zero color.
That's why you get K minus 2. It's just some fixed color.
I think it might have to be 0. Because, yes, yeah, it's a group. You have to use the 0 at the, of the abelian group. Okay, if you have, so first notice that 2 and 3 together implies that the vectors are orthogonal. Because if they are different cliques, then they will have disjoint Fourier support, and hence the collection will be orthogonal. And hence we can also normalize the vectors. It will be non-zero, so we can also normalize the vectors, okay? Now, if it is orthonormal, then notice that for every node in the switching network, 1 is at least the inner product of the reachability table everywhere, because the reachability table returns a value of 0 and 1. If you take the expected value, it will be at most 1. Okay. And in particular, this, when you express it in an orthonormal set, it may not be a basis. It may not generate. It may not span the whole space. But as long as it is orthonormal, we have this inequality. We can express. Oops, this is our A prime. Sorry, that. Oops, wait. This is our A prime. Sorry. Yes, this is our A prime. That the inner product will be at least our A prime this is just projecting the square coefficient will be at least the sum of square coefficients in any of the normal set of vectors. Okay. If we have this, then the lower bound goes like this. The size of the switching network is just sum of the number of nodes in the switching network, and 1 is at least this. Okay, I said it's A prime, so it's correct. Okay. Sum over all possible k clique. Then, if you switch the order of summation, and then notice that R A prime, this sum is at least for the contribution at the bottleneck node. Then we have this inequality. We are using so far we are using 2 and 3 to get orthogonality, and hence if we orthonormalize it, we get orthonormality, which will allow you to express the square coefficients in the orthonormal set of vectors, and hence this inequality. Finally, notice that the sum of contributions over all possible nodes will be at least the contribution at the node where you have a lower bound on. If you are here, then you will get a lower bound like this. So first, there will be n to the k cliques. This gives the first factor. Each of this inner product is going to give you a non-negligible factor by property 1. There will be non-negligible work. And the normalization gives you a loss, but the loss is bounded because the vectors are short. This is property 1, and this is property 4. The vectors are short bounds the loss. And the fact that you have non-negligible work done by property 1. Okay. If you have this chain of inequality, then the size of the graph after taking is polynomial lower bounded by some factor of n divided as after some loss raised to power k. So it will be at least n to the k when it will be at least n to the k when k is polynomial related to n. This completes the proof. Assuming you can execute the proof to get, in other words, for every clique p, you can find vector GP satisfying the 4 properties, that it will have non-negative response at certain node B prime. It is short. It will be orthonormal, or I mean, the Fourier support is controlled. That it is k-mass 1-wise independent. Okay, all right. But actually, I didn't prove anything because I didn't tell you how to construct the. Okay. Yes. Okay. Yes. The 4 properties we need to satisfy are these 4, and I told you that actually, in the real application, we don't get to k-mass 1-wise independent. We get something worse. But to fix the proof, we use a Nielsen-Wigderson design that will give you n to the k loss of cliques that pairwise intersection will be bounded by k minus 2. Okay, that's the only technicality. If you assume that, then the good proofs go just like what I said earlier. Okay. Yes, but actually if they're different, the maximum pairwise intersection is k minus 1. We can afford k minus 2, so it's almost the maximum. Okay, and to see, okay, I'm going to explain how to get. So these are properties that you can check. The most mysterious thing going on is number 1. How can you get a node that has non-negligible response? That's the meat of the argument. Then we will do, as Avi said, we are trying to focus on the computation path at setting the clique and consider the work done and try to locate something there. Okay, should I?
Sure, yeah.
Okay.
I want to mention, I mean, Reversible in his approximation method for switching networks has the notion of a cover. I mean, it's a reduction from pulling a switching network
Oh, really?
Yeah.
Yeah, okay. Let's see if it's the same as this cover. So this cover, invariant cover, well, so here's the definition. First, I will define invariant. Well, given a literal, here is a positive literal. For k-clique, it is some edge UV. Given a literal and a monotone switching network for k-clique, so and a monotone k-clique switching network G prime, I define a vector to be L invariant on the switching network. A vector is L invariant for some literal L on a certain switching network if the following condition holds. If for every node on the switching network G prime, for every node A prime and B prime connected by an edge labeled by the little L, the reachability doesn't change as you go from one truth table to another truth table. When view at the Fourier angle at G, if it doesn't change, then G will be L invariant on G prime. In other words, it fixes the progress of the change in truth table. When you, by that I mean when you view it after inner product, change it with G. If you consider truth table and consider the inner product with G, this doesn't change as long as they are labeled by some edge labeled L, then it's L invariant. So in other words, it fixes all adjacent truth tables. They are labeled by L. And it is L invariant if it holds for any monotone switching network. So it is a very strong condition. A vector is L invariant if for every possible switching network, for every possible node that is connected by a literal label L, some SUV, the truth table doesn't change when you view at the inner product at G. That's the meaning of L invariant. And then I will motivate right away after giving one more definition. So here comes the invariant cover. Invariant cover is a collection of vectors that for fixed k-clique P, I say a collection of vectors. So we are going from a single vector to a collection of vectors. This is important that actually in order to achieve points 1, 2, 3, 4, remember what we are shooting for is to get a vector GP satisfying 4 conditions. We will do that by first considering a collection of vectors satisfying 4 analogous conditions, basically 1 prime, 2 prime, 3 prime, 4 prime. For a collection of vectors, we satisfy some conditions, and then somehow we will get a vector out of the collection that satisfies the original 4 conditions. That's what we are going to do. Okay. For k-clique P, we say the collection of vectors indexed by the vertices in the clique P. So there are k such vectors. This collection is an invariant cover if it satisfies 2 conditions. First, for every 2 vertices, for every edge that is in the instance of P. In other words, for every 2 node states in P. For every 2 node states in P. Remember, when we identify a yes instance to a clique P, an edge is in the instance associated with the clique P if and only if the 2 vertices in the clique. For every edge that is in the instance of P, there will be some node that such as its vector is invariant with reversible edge. Oh, you will see why it's defined in a moment because it's defined so that the following lemma holds. This V has nothing to do with this V. Oh yeah, good. This V is W. The X is W such that GPW is UV invariant. We can use it that way, but we actually will get a vector such that this V is actually one of these, actually both of these. But it's good points that, well, so it doesn't matter how you interpret it. It will be fine in our case. Good. And such that its zero Fourier coefficient is 1. Sorry, it's 1. Zero Fourier coefficient is 1. This one is 1. But the empty Fourier coefficient is 1. The empty Fourier coefficient is nothing more than the inner product with the empty character. The empty character will assign 1 to every possible coloring. So it's a constant 1 vector in the inner product space. So in other words, I want the vector that assigns 1 everywhere to be 1, to have an inner product 1 with all the vectors in this collection.
G is going to be monotone, any positive function?
G positive. No, it needs not be. There's no such restriction. The reason that this definition makes no sense unless you see how it is used. It is used to give a lemma that will identify a bottleneck node on the computation graph accepting a click P. The lemma goes as follows: that if you, for any click P, and if you have an invariant cover for the click P, assuming that you have such a thing, then for any path that accepts the click on the switching network, I want to locate the bottleneck node by, as follows. I want a node on the computation path. I want a node B prime P that is on the path, and 2 nodes on the vertex, such that in the invariant cover corresponding to these 2 nodes, I want the inner product of the difference of the vectors. When you inner product with the reachability table as the bottleneck node, it will be what we need, a non-negligible contribution. We want this in property 1. In other words, we are going to get the vector GP we want to get as the difference of 2 vectors in this collection. We are going to come up with a collection of vectors satisfying certain properties, so that if we take the difference of any 2 vectors at certain point, then it will give you a non-negligible contribution. We are going to find a vector this way. So in order to find one vector, we first go to, in order to find one vector satisfying 4 properties, we go to a collection of vectors satisfying 4 related properties. This way, the difference will give you the original vector satisfying 4 properties. That's what we are going to do. Okay, and then I'm going to explain how to do the why you have these 2 conditions. So here's the discrepancy in progress lemma. It's better to draw it on a board. Okay, so if we want to show that for every computation path for every computation path from the source node to the sink node, and P prime accepts P, there will be a bottleneck node. And also 2 vectors in the family, such that the reachability table at the bottleneck node with non-negligible response to the difference at okay, this is what we want to show. Here's the proof. First, what we are going to do is you lay out the path, okay, from S prime to T prime. We're going to draw a 2-dimensional table. The columns are indexed by vertices on the accepting path P prime that accept the click P. The rows are labeled by the vertices in P. These are vertices in the click P. And the A prime, the entry of the table will be the reachability table at the node inner product with the vector that adds. This will be the entry of the table at row V and column A prime. So we are going to build a 2-dimensional table. The columns are labeled by nodes on the accepting path. The rows are labeled by the vertex in the click, and the entry at row V, column A prime, will be the reachability, will be the inner product of the reachability table at the node A prime and the V vector in the collection. We consider this 2-dimensional table.
So initially the first column is all 1.
The most important observation is that first, since all instances can reach the source node, so the first column will be all 1. Since there are all no instances, at the end, they will be rejected. So the last column will be all 0. So you will have k vectors, k numbers. They're going from
Why are the last ones zero?
because this because reachability table at t prime of every c is 0 for every c. Because for every c, it is a no instance. The no instance cannot reach the sync node. It cannot reach the sync node, so the reachability table will be false. If the reachability table is false, then its inner product with any vector is 0. So you have k numbers. They go from 1 to 0. And okay, the reason that it is, okay, they go from 1 to 0. And we want that at every transition, we want that at least one player cannot move. In other words, I want to make sure that if you look at this column and this column, at least one of the numbers will be copied from the previous column. If you,
That's because of the invariance.
there's the definition of invariance. So for example, when you make a transition from this node to this node, I want to make sure that at least one of the row doesn't change. The other things can change. So the first condition in the invariant cover is to ensure that at least one row doesn't change. And the second condition is to make basically to correspond to the fact that at first is 1. That's the two. That's why you come up with the two properties. Once you get this, then it is not hard to see that at some point there will be two vectors that differ by at least 1 over g. In other words, there will be some column such that there will be two entries in the column. The difference will be at least 1 over the length of the path, which will be which will prove the lemma. This is really not hard. It's an easy proof. So if you know how it is used, then it makes more sense why you come up with these two. Okay, once you prove this will finish. So in other words, originally we want a vector GP satisfying 4 properties. Now we want a family of vectors. We want a family of k vectors satisfying 4 related properties. Then we apply this trick, then we will get the origin vector. It's the difference of sum of the two vectors. Okay.
So you will have to prove that each of these is short also.
We will also have to prove that each of them is short. And okay, so we will prove 4 related properties. It's really not hard to figure out the 4 related properties. It's not hard. And let me at least mention what the family of vectors look like. It gives you some information. Okay, so the family of vectors will look like this. So we want to for every clique P, we want to construct a family of k vectors, 1 for every vertex in the clique. So we are going to construct the family of vectors. For every vertex V in a clique P, we define a script C vector as follows. Well, we want to control its support, so we want the definition to satisfy a certain condition. So it will be 0 if it doesn't satisfy a certain condition. The condition that we want it to satisfy is that the coloring C, when restricted to P, has a monopoly. Whereby monopoly of a coloring, I mean a coloring has, now the color when restricted to a set of vertices of size K has a monopoly if exactly one color class has more than one vertex. So a coloring from K to K minus 1 has a monopoly if exactly one color class has more than one vertex. In other words, if the set of color all colors would appear, but some colors would appear more. If the only color class that appear more than once, there's only one color class appearing more than one, then it has a monopoly. So if yes, the C in k minus 1 such that the number of coloring such that its inverse is bigger than 1 is exactly 1. If the number of colors lead to C in k minus 1 that has more than one vertex mapping to it is exactly 1, then that color, those vertices
And V has to be one of them.
are the monopoly. Oh, and V has to be not one of them. Okay, so we want it to satisfy certain conditions related to monopoly. The intuition is that its complement is like would be a clique, so you are counting cliques somehow. That's the point. And okay, if it has a monopoly with mu vertices, and the monopoly does not contain V, this is the support of the vector script C, and it will be a certain expression, combinatorial expression, with a certain scaling factor. The point is that if we set things up this way, then it will this vector will be an invariant cover. In other words, it will be UV invariant. We control its support, and it will have one. When you take the inner product of all one vector with this vector, it will be 1. That's why we choose the scaling factor so that it will have 1 when you take the inner product with the all one vector. Okay, so it will be an invariant cover. It's not hard to see that it depends only on P. It's by definition, it depends only on current on P. And it agrees up to degree k minus 2. In other words, this means that the difference of any two different vectors will be k minus 2 wise independent. This is what I'm saying here. And they will be short. Then if you check all this, then this finishes the proof. Okay. So what we have done, we prove a title bound for the k-clique problem, for the computational problem of k-clique under the Morton restriction on the model of switching networks, and using the technique of Fourier analysis and studying combinatorial invariance. And is a question that this time I'm asking you that can we get more lower bounds by considering different computational problems under different restrictions on different computational models using different techniques. Okay.